Professor Peter Littlewood on Polariton, condensation, and collective dynamics. Peter was for many years in Bell Labs, where he overlapped with Rama, and then he was in Cambridge University and has recently moved to Argonne National Lab. So.
Thank you very much. So thank you for inviting me here. It's on now. Good. And yeah, it's a great pleasure to come here, of course, in honor of Ramas, who, as was just mentioned, I met him many years ago, longer than I care to remember, and longer than in fact, longer than I'm able. I suspect that he can remember many farther than me. Robert, you give us all hope, actually, because you're ageless, as far as I can say. You seem to me to be more or less the same as when I first met you. but no more. So the thing I realized that I'm most embarrassed about is, despite the fact that we've talked on so many times and worked on the same field for so long, I don't think we've ever written a paper together. Right. So, well, maybe we should fix that at some time. So I think we always fought to a draw, really. That was the point. So I'm going to talk about something very different. I was almost inspired by Rao's talk to change subject and talk about oxides, but I decided instead that I'm going to ask for your indulgence. So I'm going to talk about a topic which is probably not very familiar here, so that means that I should give quite a lot of introduction. But my second part of my indulgence is that, in fact, I'm forever talking about this subject to an audience who's never seen it before, and I never get past the introduction. So today, however, I'm going to go really, really fast through the introduction so that I can talk about some of the stuff that we've been doing lately. Almost all of this work is still in Cambridge, actually. I'm currently a PhD student, Richard Brierley, a postdoc, Cele Creatori, and actually with an experimentalist, Richard Phillips, in the department, and closely coupled to Paul Easton in Dublin. And I will refer to some work done previously by some of my colleagues in Cambridge, all of whom have now moved on to greater things. Okay. There will be a bit of background. But really what I want to talk about, I suspect, in the context of the current discussions, is really the Higgs boson. You have to get that into your talk these days. You may not know this, but the Higgs boson is simply the... You people did it long back. Well, it is. So the Higgs boson, so I'm really going to talk about the amplitude mode in the context not so much of superconductors, which has a long history in condensed matter physics, but I'm going to talk about, if you like, collective dynamics of a system which is in fact a really model system to study BCS-like models, mean field-like models of correlated order. And so I'll spend some time talking about the background of this subject, and then try and get into some of the details. And there's a mixture of stuff, some of which is trying to understand how to excite collective modes in these systems, and to understand whether those collective modes are in fact stable, whether they can decay, what kinds of finite Q instabilities there can be. But I also want to talk about state preparation, because that's the other thing you need to do in these systems. You need to be able to prepare quantum states and put the system into the initial state we would like, so you can then let it go and watch its dynamics. So what is the topic? So here's a quick introduction to what I'm going to talk about. I begin with an exciton. An exciton, as you will all know, begins by taking a semiconductor with a chemical potential lying here, so that at low temperatures there are no carriers, finding some way to excite an electron-hole pair, and having that electron-hole pair bound by the screen-Coulomb interaction to make an exciton. Of course, an exciton is just a hydrogen atom, or something like a hydrogen atom in a solid. However, because it's bound by the screen-Coulomb interaction, and the particles don't have the same mass as in free space, the size, the Bohr radius, and the bonding energy, the Rydberg, are vastly renormalized from what they would be in free space, and typically we'll be dealing with 3,5 or 2,6 semiconductors where the binding energies are a few millivolts and the Bohr radius is 7 nanometers. So you make atoms which are big and fuzzy. Okay? Now, for about 40 years now, actually maybe getting on for 50, people have fantasized about taking these atoms and doing coherent physics with them, and in particular, if these are atoms, well, what do you do with an atom? You can make a superfluid, a Bose condensate, something like that. So that has produced a vast amount of work over the years, generating all kinds of interesting things, electron hole liquids, something that Morris worked on, the metal insulator transition understanding, and in fact understanding transitions between dilute and the dense limit provided a foundation by which we now understand the BCS to Bose crossover, but in very different systems. So a lot of the early work went into this. The experiments have been exciting, but have not actually, in these systems, ever generated kind of repeatable, reproducible evidence for condensation, although every few years we feel we're getting close. One of the reasons is quite simply that if you make an exciton in a direct gap material, it will typically decay to a photon, and therefore they don't live very long, and establishing thermal equilibrium in a population of these things is hard. Okay. So there's a decay process. But of course, if you, that decay process could be followed, or absorption happens in a quantum mechanically coherent fashion, then you're simply making a new particle. A new particle you can think of as being a dressed photon or a dressed exciton, but this is kind of a 50-50 mixture, and this is typically called a polariton. Now, that, if you can stabilize it, is in fact very interesting, because this is a really light mass particle. Typically, the effective mass of the polariton confined in some quantum box is around 10 to the minus 4 of the electron mass, and since the matching of kinetic energy with thermal energies are what give you the overlap to something like BEC, you imagine that you don't need to have very many of these things in the box before you can get a decent amount of condensation. So in practice nowadays, how do people do this? I'm going to talk about two-dimensional systems. You begin with a quantum well, and you can create excitons that run around in this quantum well. They will be bound down below the particle hold continuum by the binding energy. This is, if you like, just the 1s exciton, but there would be 2s, 2p, etc. in the middle here, which I've just ignored. This binding energy is a few millivolts. This gap, of course, is typically 1 to 2 volts, depending on your semiconductor. Okay. And I've just drawn the center of mass spectrum of a particle moving in this two-dimensional box, energy versus momentum. If I want to couple this to photons and then confine the light, I need a photonic cavity, and I need mirrors on the box. I'm not going to discuss how you do that, but the technology for that has been adapted over the last 20 years, really, and it's now possible to put mirrors on an optical cavity and have a two-dimensional guided wave photon mode that lives inside. Here's what the wave function would look like. It's just basically a half wave. You simply fix the momentum of light to be here, and if you fix the momentum of light just right, you can tune this frequency so that it's degenerate with the exciton. It doesn't have to be exactly degenerate. This is complicated, this is detailed. You want to tune these things to be close to each other. Of course, this dispersion curve is very steep, because if the photon starts moving in the plane, you rapidly, of course, asymptote to the light cone. So this parabolic minimum is very steep. And now, of course, we manipulate these things, we get them to be degenerate, and you couple them. And when you couple, you make two modes, generically called lower and upper polaritons. And the wave functions are really quite straightforward, at least in the dilute limit. This polariton wave function is some linear combination of exciton and photon. If you start off at degeneracy, it's 50-50. You just have the in-phase and out-of-phase components. As you move out to larger momentum, you have either you turn into an exciton or a photon on these two branches. The last thing which is important to understand if you want to look at experiments is that while these mirrors may be good, they won't be perfect. Eventually, the polariton will tunnel through them and emerge on the other side as a photon. And when it emerges as a photon, if the mirrors are flat, just like in any photoemission experiment, parallel momentum will be conserved, and therefore the angle at which the photon is emitted will reflect the momentum in plane. So that means that a particle which is moving this way will come out at that angle, something moving here will come out at that. But if, however, you've got particles which are sitting at zero momentum, then they will move vertically towards you. And of course there's a history of this which goes back to work beginning, I think, really with Claude Weisbuch and others over the last 20 years. And simply the samples, the preparation methods, everything has just got better over that time. And by a process of continuous improvement, we've now ended up with an ability to really control these things very finely. So the idea is you do an experiment, and the ones I'll show you is you pump with light similar up here, you generate a lot of electron hole pairs. Most of them go to places you don't know. We combine a few of them, however, will scatter down here and eventually trickle down. And if you're lucky, they will develop a thermal distribution sitting at the bottom of here. And as I say, this effective mass is very light. Okay. So here's some data. This is data from the group Grenoble, a collaboration with Lausanne and actually with Cambridge, where we were doing the theory modeling on this, of measuring from the bottom of that dispersion curve. Here it is, that's the bottom of the parabola. You have a system which is very cold, kept at 4 degrees, at least that's the base temperature. The temperature of the polaritons is a little higher, but at low powers you populate a distribution in the bottom. As you go to higher powers, you see that this actually gets sharper. It gives you a blue shift, which tells you what the density is, so you've got that calibrated. And if you just look at N of K, you see the development of this peak. Okay. So this, of course, is very reminiscent of what you would see in a cold atom experiment, and carefully plotted for the editors of Nature, even with the same color scheme, so that it would... and then, of course, you want to look at that peak and you want to say, well, is it really coherent? And you can do a coherence measurement simply by taking the light coming out, interfering with itself. And here's an interference measurement where you interfere in a Michelson interferometer, an image with the inversion of the image. This is below the onset, this is above it, and you're getting about 50% coherence across a spot of order 20 microns. Again, very early data. It's now got much better. Some later experiments now shows you very sharp lines, very well-defined modes. Other things you can look for, people have found vortices. Here's one. It turns out that these are you can make half vortices in these systems, and the reason is, of course, that light is polarized. So you can have a vortex in one polarization and not in the other. That corresponds to a half vortex. Those have been seen. So it's the analogy is direct with helium-3. You can look at the spectrum and try and look for linear modes. This is claimed to see it. I don't really believe that, actually. Bogdanov mode living at the bottom here. You can even do nice experiments. These are some, I think, Parisian experiments in making a superfluid. You could prepare, of course, a condensate by driving the laser. Here it is. It's now being prepared with finite momentum, so it's moving. Here it hits something, and here it comes back on the other side and reconstructs. Okay. So there's now a lot of experiments now demonstrating the sort of classic phenomena in equilibrium or near equilibrium that you want to see. When we peak in the momentum distribution, phase coherence, vortices, superflow are being seen. Okay. That was my introduction. There's a lot more that I could talk about, but I won't. Okay? I list a few things that immediately come to mind from the point of view of a theorist. Okay? Firstly, this is a composite particle. It's a mixture of electron hole pair and a photon. In what sense is this really Bose condensation? You would guess, of course, that the answer there depends on the density. If you make a particle which looks like a boson but which is of extremely light mass, it's very big. So a polariton, if you want to think of it as a particle, is a few microns across because it's basically dominated by the wavelength of light. So that does not behave like a dilute Bose gas for very long. As you add more particles in the box, the particles can overlap, and you actually get a BEC to coherence state crossover. I may say a bit about that. This is at much lower densities than the limit of where the excitons themselves will begin to collide sufficiently to break up. So what we're actually dealing with here is a system where you have some bosons, but with a long-range interaction. So it's a rather unusual system. There's, of course, 2D physics. There's a lot of stuff to worry about associated with non-equilibrium dynamics, because the experiment I showed you, we were shining light on the sample, there's no trap, things are diffusing around, it's being pumped and decaying, so how on earth can you maintain a condensate under all of that? And that produces some kind of knotty problems that are sort of worth a series of lectures, but one can indeed understand all of that as well. But what I want to talk about is what you can do by preparing out of equilibrium condensates, in the sense of the way people do with cold atoms and quantum crunches, and to try and see if one can hope to use these systems to study quantum dynamics of a many-body system. So I should tell you what the many-body model is. Okay? So for me, the theory begins here. So for me, I like to think of excitons as spins, because you can either have them not there, which is an empty state, or there, singly occupied state. And I'm going to assume that if you put two of them in the same place, they don't like that. Now, some of you will be aware that, of course, you could make biexcitons. That's the analog of H2. And fine. I mean, I can just generalize the model to include that if I wish. We'll get almost all of the physics that we will just by considering these. This, of course, is easily enough just remodeled as a spin. Okay. And so the rate is, and the spins, of course, are flipped by absorption emission of a photon, and therefore your Hamiltonian has a photon field with some characteristic frequency omega, a bunch of two-level systems representing the excitons, which I've put at sites because actually these systems are typically very highly disordered. The excitons don't move, we might as well treat them as localized, and so this is just SZ. And of course the magnitude of SZ tells you what is the occupation. And then this Rabi coupling, which involves absorbing a photon and flipping the spin up or flipping the spin down and creating the photon, with a coupling constant G, which is a material-dependent constant. But notably also, something that I fed into the analysis here is this number n, and that simply takes account the fact that if I have a photon confined in a box, it's nonetheless something which its wavelength is going to be microns. Excitons are nanometers apart. There are a large number of excitons that interact at once all with the same photon field. And that's this factor n, so this is typically photon size over exciton size to the power d. And this is a number which is much bigger than 1. All theorists, homework, should know that faced with this Hamiltonian and the limit that n goes to infinity, the ground state is easily specified. It's called a coherence state, or BCS in another language, namely that the wave function associated with this is a coherent state of photons, a coherent state of spins, and the way to think about this is that, of course, you have spins because these omegas here are weights. If these parameters are all real, or if at least there's only one independent phase, then these spins are simply processing self-consistently together in the coherent field produced by the photons. And in the limit that n equals n goes to infinity, this is the exact ground state. And just like a classic BCS-like problem, the transition temperature is then fixed by the coupling constant of the density of states. And we're done. Yeah.
This Hamiltonian seems to be restricted because nothing can flow.
Right. So the point is, if I want to deal with decoherence effects, this Hamiltonian has a conservation law. Right? So the number of excitons plus photons is conserved. Okay? If I want to deal with an open system and connect this to the outside world, I'm going to have to introduce baths. Right. So I've made the rotating wave approximation here. That's important, and actually has the effect, by the way, this model is integrable. If you care, it's never helped me, because the answer is no. It's a Richardson-Godin model, and you can contemplate the answer, but I've never succeeded in really extracting anything from it. But nonetheless, it's so you're right. And the fact that, by the way, the fact that I'm neglecting spontaneous emission is of course fine because I have a system which is very far from equilibrium, right? So I don't need to worry about thermal equilibrium with photons at 4K because these rotating waves are happening with an energy associated with a couple of electron volts, right? Yeah, but nonetheless, I mean, there are various approximations being made here. For the students in the audience, by the way, I will remind you that there are three ways of actually solving that problem. Route number one is, here's the Hamiltonian, here's the variational wave function. It's got a bunch of parameters. You can minimize the free energy a la BCS. And then what you will do is you will get an order parameter equation with a renormalized spectrum which has a gap in it. The gap in it is caused by the entrainment of those spins. And a sum rule which is used to fix the chemical potential mu, which just tells you how many particles are in here. Okay? This is very BCS-like in a very standard way, although admittedly it's completely bosonic. Right? So it spins. There's another way of doing it, which people do in optics, which is to go to a conventional two-level system notation, and then you say, if I think about these spins, what I will do is I will just consider the polarization as one degree of freedom, the amplitude, the occupation as another degree of freedom, and of course the photon field is another one, and I will treat them as scalars. The treatment of scalars in the semi-classical approximation is precisely analogous. Well, it's precisely exactly the mean field approach. So again, you can solve the Heisenberg equations in motion in that limit. You can couple them, and again, of course, you get the BCS gap equations. So it's just another way of doing the same thing. Although nowadays, since I've learned that the real way to present this is, of course, this. I've generalized this actually to multiple modes so that we don't have a single photon mode. We have a continuum. Then, as you know, the right thing you do, you write down the action. You minimize the action around the saddle point, and you get the same equations again. Okay. This is, of course, a useful way to proceed if you want to go forward and do other fluctuations. Okay. But I also point out that it would have been understood very well by this fellow. That's Huygens. Huygens discovered that Huygens was building clocks, and he discovered that they could synchronize. And the method that we're really describing here is something that can be done in the classical limit in a very easy way. Take a few metronomes, which are nice nonlinear oscillators, couple them together by putting them on a piece of wood on a couple of cans, set the whole thing going, and of course you will discover that this very easily synchronizes. It synchronizes into a phase-coherent ferromagnetic mode, and so these are your quantum oscillators. The mode, but you would also see that the table starts rocking backwards and forwards. That is, of course, the photon field which is supporting all of this. Okay. The equations of motion I just gave you are entirely classical. BCS is a classical theory. Right? BCS does not have any quantum mechanics in it. I mean, not by the time we're looking at the solutions. It's all semi-classical. The equations of this, I mean, you can just take the equations of coupled classical spins and they're these. All I have to do is I have to do some, if I were to put in temperature, I have to figure out how I'm going to do that. It's a mistake to believe that, I mean, as actually the people with ADS-CFT have done these days, that if you produce BCS, at the end of it you've invented quantum mechanics. You've not. So it's a completely classical theory. So, how does that actually happen? If you just solve that problem, what you find is you've got two branches. Here's density, zero density here increasing. You've got an upper and a lower polariton branch. Chemical potential lies down here. It rises at some point, it hits the bottom branch, and at that point you begin to get the emission of coherent light. I did it here actually where those things are attuned to the exciton and photon, attuned to be at the same energy. If you detune them, you get into the regime where you think about Bose-Hubbard models. So here again is the phase diagram. This is inverse temperature. This is density. if you go to a situation where they're sufficiently detuned, so this means that the photon energy is much higher than the exciton energy, then we're seeing here basically the first Mott lobe of a transition, and this transition inverts back here, and there's a critical point that will take you from this discontinuous jump to another one. So this is, of course, familiar physics that we see in a very different language that is sort of well known. Okay. Now, I'm talking very fast, but as I say, you have to indulge me. I gave you a coherent state wave function that clearly is not BEC, right? And the answer is easily sorted out. As I said, the coherent state regime applies when I have sufficient number of particles in the box that they're overlapping at very long length scales. And then I have a mean field description which will give this coherent state formula for TC versus density. BEC, of course, would tell you something like in 2D, and let's not worry about Koslitz Thales at the moment, a transition temperature which will vary linearly with density divided by the effective mass. And of course, that's a very steep line which rises up here. And it's very steep because the mass is very small, and consequently the point where it crosses over is at very, very low densities. So if you want to do a real theory of this, which you can do, it involves going back to that third method I said, calculating the fluctuations in a way which actually I think was done. Look at Mohit's review article, actually, on how to do that. Then you can see by changing the effective mass, you can see this BCS-like two Bose crossover. These parameters are just for different masses. At very low mass, you're in the BEC region, then you cross over to BCS. And here, because actually there's a finite number of states, you cross back to a region which was lately being dubbed BEC of photons, and actually has been seen in some experiments in Bonn. Okay. So you get a BEC to, but all of this, even though I'm calling this BCS, doesn't mean that I have pair-broken excitons. They're still behaving in a kind of strongly interacting bosonic fashion. And the range of data is typically over here. We're actually well into this strongly interacting many-body regime. Okay. Right, so non-equilibrium dynamics. I'm just going to work on semi-classics, actually. Okay. So we have a model I've rewritten it in a different way. Here again are the photon modes, but now I have a continuum spectrum, as you should. Energies of the spins, coupling of the spins to the photons of this form. And we can imagine just doing semi-classical dynamics. As I say, remember that the ground state solutions of the semi-classical dynamics correspond to BCS, but I could, for example, pump the system, describe how to pump it in a moment, that, say, puts in some photons at a particular momentum P. Those photons will then couple into the excitons because they begin to drive this term, and generate a double occupancy, and that all of that feeds back. So how am I, so that's a sort of generic kind of experiment that one would like to try and do. And we'd like to follow the dynamics on timescales faster than dephasing coupling to the environment happens. And it's very much like a quantum quench in cold atoms. And in a crudely all that happens, we start with an initial degree of initial state, and we're just going to project it onto the exact time-dependent eigenstate, which of course we don't necessarily know. If the perturbations are small, you expect to see a linear superposition. If the perturbations are large, it's difficult to know what to expect. Okay. But here I want to map across, go back to the exciton spectrum, so the Polariton spectrum in the condensed phase, and map it across to you in something which is familiar. Okay. So here's a superconductor, and if I look at the spectrum of collective modes, I have a body with a phase mode. That enters, that's a very steep mode, and that enters the continuum of excitations, particle continuum at 2 delta, the momentum which is the inverse of the coherence length. And in addition, you also have a mode which is the amplitude, a collective amplitude oscillation of the superconductor, which in a BCS S-wave superconductor comes in like that. This is the spectrum in at least a theoretically calculated spectrum in a Polariton condensate. This was the upper and lower branches. We've gone into the superfluid phase, so I've got a mirroring of all of these modes. There's a continuum that arises here essentially because of disorder. There's a dispersion in the spectrum. And you see that the right and physically right identification of the upper Polariton branch is as the amplitude mode, and the lower Polariton branch will turn into the phase mode. Because we're in a regime which is bosonic all of the time, these modes are preformed. In a superconductor, you only make amplitude and phase modes. Well, I mean, in a BCS superconductor, you only make amplitude and phase modes when you form the pairs, and that happens at the transition. Here we have pairs formed already, it's preformed pairs, and you have a mode, these two modes, and the development of coherence appears here. But nonetheless, we can imagine driving these. How is one, however, going to pump the system? Here's back to experiment for a moment. And you see, the problem with creating pumped excitons, not sure how far I have to go back. If I want to create a population here, if all of the excitons have the same energy, it's easy. I drive it with an external field, and I produce a Rabi flop from everything down to everything up. If these E's vary from site to site, which they do because I have a lot of disorder, if I produce a Rabi pulse which is valid for one energy, it won't be valid for another, when I won't be able to get a coherent population. That was solved many years ago by NMR in a method which is called adiabatic rapid passage, which simply involves applying a chirp pulse, so you take two levels which are of different energies, but because the frequency is changing in the rotating frame, these two levels are brought close together. You turn on a pulse to couple them in that regime, and if you do this adiabatically, you will of course transfer the spectral rate from this mode into that mode, and that gives you in principle robust population inversion. And this is not, doesn't care about whether you are exactly in degeneracy with the modes. Proof it could be done. This is work from Richard Phillips' group. Another group in Toulouse has done something very similar. Here's the theoretical model, here's the experiment. This is what you get with the conventional Rabi pulse, and this is done, by the way, on a single dot. And this is done with ARP, showing that you really can produce this, and they are now working to improve this for arrays of dots and then put them all in cavities. What would you expect to see if you could do that? Well, here's an example. Here's a bunch of levels. Let's suppose that we populated them with something that looked like a Fermi distribution. Okay. Parameters are available. You can do that, so you produce this blue population, which looks like a Fermi distribution at 0.6K. However, this would not be the ground state, because when I turn on coupling of these dots to each other via the photon field, I will generate a gap here, just as you would from this coherence. So what do you expect to see? And this is a prediction of what you should see as a function of time. Here's the pulse, turning the levels on. You don't develop any coherence at all really right at the start. There's a small amount here, just nucleating it. And then after a while, however, you begin to see these oscillations. What are these oscillations? Well, first, of course, what you realize is you've got a system which would like to become, if you like, a superconductor and open up a gap. So it tries to do that. It gets itself organized in a way to do that, but it has too much energy. So it has energy left in the final state which it has to put into something else. And so the coherence develops, and then the coherence oscillates. These are amplitude mode oscillations of the order parameter. And they're gradually bringing down here because we've got it in a cavity with the decay. Okay. So this is a more or less precise analog to a quantum quench. It's interesting to ask whether they're stable. Okay. At the mean field level, if I don't have space involved, I can just set up a K equals 0 mode, but will it actually be stable? There are all kinds of reasons to believe that it won't be. After all, the Higgs decays, it doesn't last for very long. Those oscillations, by the way, are the precise analog of the Higgs boson. So one can look, for example, firstly in linear response. Now the system is oscillating. I can ask, is the response function positive? Okay. So we can look at that. And here, if you have the modes which are unpopulated, we're just tuning through the cavity frequency. You see the conventional modes. Here, what you see is you get a region of gain. If they're populated, where is that gain coming? Well, actually, typically it's occurring at finite K. The way to look at that, again, technical for theorists. For the mean field theory, there are closed-form dynamical equations. For example, Barakov and Levitov have used these. Altshuler also. They're periodic in time. And so you've now got a system which is being driven periodically. And when it's being driven periodically, if you linearize about that, you'll get a quasi-energy spectrum. And that so I'm going to look at the quasi-energy spectrum. But of course, if the system wasn't being driven, I would just get the usual band structure, so I would expect to get the usual Polariton spectrum. What happens if I take this thing here and do it now when it's being driven? Well, interestingly, you discover, of course, that the modes will always multiply, so here's the phase mode. But of course now, because it's in a periodic potential, the phase mode repeats very many times. These two phase modes meet, and where they meet, they attract, and they generate an instability. Around the bottom of the amplitude modes, it turns out also that where the modes meet down near here, you also generate an instability. What are they? This one is something which to optical people would be called an OPO, an optical parametric oscillator. You've got an oscillation which is happening up here. It can decay into a pair of phase modes. This one here is associated with the fact that you've generated, it turns out, phase separation. Namely, you've got an attractive Bose gas. And so this is done in one calculation. This is the same spectrum, however, calculated just for the Bose gas with weak attractive interactions. And so that's exactly the analog of that. Okay. And furthermore, if you drive it further and see what happens, all of these modes, this is time and this is space, generate interesting spatio-temporal patterns, at least at the semi-classical level, which looks like spatio-temporal chaos. Okay. These are some few things that one might be able to see. Well, in some sense, superradiance is built into this. So the first thing that I showed you, remember, where I just pump the system, a while later it begins to develop coherence and to oscillate. You could call that superradiance. It's not superradiance in the classic sense of a one pass of a wave through an excitable medium. But it's all the same phenomenon, right? So as I say, I always call this the Dickey model, despite the fact that over the years it's been labeled the James Tavis Cummings model, so that more people could get their name on it. The physics and the underlying ideas go all of the way back to Dickey. How much longer do I have? 2 minutes. Good. Okay. So lastly, I just want to talk a bit more about state preparation. Because having seen that we can actually prepare simple states, just invert them, can we prepare things which are more complicated using ARP? Okay. So for example, consider that you actually had a dot which contained two excitons that had an exchange coupling. That exchange would probably be force mediated in this context, right? And you could generalize this to an array or a chain or something like that. Okay. Can you make use of this exchange, which of course naturally entangles spins, to pump yourself into a well-defined state? Okay. So the first thing is, if you just try and do inversion as a result of these, with exchanges, it turns out that even if the exchange is on, You can still invert. This is good inversion over here. These are Rabi oscillations appearing down here. Why is that happening? You can do it with Jordan Wigner, but I won't bother. Basically what you have is you have a set of levels, which is a function of time, because a chirp pulses on are crossing, and you can cross them in particular orders, and if you put the pulse on here, you'll end up going from this one to that one. If you put the pulse on the whole lot, you go from the empty to the full state. Okay. Can we use it actually for a two-state system, and the simplest one to look at would just be something which has a single triplet splitting. The natural ground state is T minus, because that's the one which is unoccupied. The singlet here, the singlet state doesn't couple, but of course there are two others. There's T plus, which is all up, and there's T0, which is the interesting one. And in principle, you see that it's possible to take a double dot system and couple it from there to there. And what I'll stress is that we focus on mostly trying to do these things in real numbers. So we also believe that in systems where you have inbuilt interactions, which you can do, we will be able to do this. So now I really will stop. Okay. I hope I've convinced you at least one thing, that there's a sort of some interesting stuff going on in this field. You should think of it as a many-body subject, right? Because actually we are in limits where we have strongly interacting two-level systems. In a different regime, you get either in cold atoms or in something else. And there's also some real possibility here of doing far from equilibrium physics, quantum dynamics. This is, of course, very close to the cavity QED approaches, which are typically done in microwave, but with superconductors and spins. And those of you know that, will know that the Hamiltonians are interchangeable one way or the other. So then I'll stop, and thank you for your patience.
What's the typical decoherence time of these states?
A few picoseconds.
So if I understood you right in the last part, the pump mode is put at time 0.
Yeah, so the answer, the probe, so that you don't even need to look at the probe, you just look at the radiation coming out. Right, so what you pump it at time 0, sometime later you develop the coherence, and then the coherence will decay. So and actually you will just see that in terms of radiation. So if you like, what happens is, according to that, you don't get luminescence, right, because everything's out of phase. And then, however, the oscillators all line up. You get, if you like, a super radial response, where you get a burst of coherent light that then rings down.
Is it appropriate to ask the efficiency of such? Is it like low?
Well, I'm not sure what I mean by efficiency. I mean, I suppose there are numbers of ways of doing this. I mean, the object that one has made in thermal equilibrium is a laser at some level. These are very low threshold lasers, so in that sense, they're really efficient. So you're far below the regular threshold for inversion. So the amount, because of this only works if you're not putting very much power in. If you put lots of power into these systems, then, all kinds of incoherent processes turn on that you don't want.
Are the experimental parameters good to have Josephson-like phenomena?
Yeah. Well, yeah, they are. So for example, the easiest way to get Josephson-like phenomena is to have coupled cavities. And so experimentally, people are beginning to work on that. You can put a grating on top, and therefore you can split off cavities, and you can have them talking to each other. So indeed, I'm not convinced I've seen real Josephson-like phenomena yet, but it seems to me that the experiments are close enough to be able to do that. Yeah.
There was no kinetic energy term for the excitons.
Right.
As a cited.
Right.
That's not important.
Well, the real reason it isn't important is that, if you like, the photons do all the work.
Okay.
So even if so firstly, most of these systems, the excitons really are to be thought of as localized. Right. Disorder. Standard disorder. So in fact, the data I showed you, I should have mentioned, is not on gallium arsenide, but is on cadmium telluride. Cadmium telluride works better than gallium arsenide because it has a larger Rabi splitting. but cadmium telluride is highly disordered. But if I wanted to add kinetic energy, which you could do, what one should remember is that the lifetime of the systems we're looking at is measured in picoseconds, and on that time scale, the excitons won't have moved hardly a bit.
But this disorder is not large enough to localize the polarity.
But it's not large enough to localize the polaritons because the polaritons have a much lighter mass. So the disorder in some sense is small. So we're typically dealing with quantum wells with a disorder in the exciton line width, which is 1 to 2 millivolts, which is much less than their binding energy. So that they're still to be thought of as atoms localized in traps. Right? Yeah.
Just to elaborate on these questions, towards the end of the talk, you did have exchange, right?
Yes, that's right.
So that's a form of halving, I guess.
Well, so there are two ways of getting exchange. You can get exchange from tunneling, which you can. The other way you can get exchange is by incorporating local photon modes which are not part of the cavity, which will basically be Forster coupling. Okay, right. And that was what I was really doing, and typically Forster coupling is going to be bigger for these systems. So one can make Forster, so the interesting thing is that the Forster coupling is in fact going to be substantial. And then the question is, how do you tune that? You can make double dots, and people have played, you may know that there's a whole industry in trying to make Forster coupling work so that you can use it for energy transfer in various devices. So it's a